and they are kind of related to each other because they're both square root graphs, so they'll have some similarities to them. But we're going to start with the square root graph first. So it says the parent for the family of functions, which was the square roots, is f of x equals the square root of x. So if in functions, parent is the basic, and then we kind of build off of that. So our family of functions we're dealing with is the square root. Since you have the square root of x, it says the domain is blank and the range is blank. So when we're talking about the domain and you have a square root of x, and I'm just going to write mine underneath here. What do we know about the domain when we have a square root function? So what has to happen with that x value, or what can't happen with the x value? Ollie? So it's allowed to be 0, but it can't be less than 0. So this number underneath here isn't allowed to be less than 0. So we say if it can't be less than 0, then it has to be greater than or equal to 0. So because it's a square root, you can't have a negative number underneath the square root. Therefore, x has to be greater than or equal to 0. And for the domain, that's when we usually say it starts at 0 with a bracket, because it is allowed to be 0. We can take the square root of 0, and it goes to infinity. So then the second part says the range would be the y values. So if you plug positive numbers inside here, so you have a positive 1, a positive 2, a positive 3, a positive 4, a positive 5, a positive whatever, what would your answer be if you take the square root of 1, you take the square root of 4, you take the square root of 9, you take the square root of 25? What kind of answer do you get? So, Holly, what is the square root of 1? What's the square root of 4? What's the square root of 16? What's the square root of 25? What's the square root of 100? What are all those answers going to be? So she said positive or negative, and I would say typically yes if we're solving it's positive or negative. However, if this square root is just a square root and it doesn't have a plus or minus already assigned in front of it, then it's always just a positive answer. So a square root, if it has a plus and a minus sign in front of it already assigned there in the equation, then we have a positive or a negative answer. But otherwise, it's always just a positive answer or greater than or equal to 0. So our range is also from 0 to infinity. So the domain has to be positive because we can't take the square root of a negative number, but that's going to make the range then also positive. So we're going to see if we can graph this by making a little t-chart. And we're going to just pick some good numbers that you would use for a t-chart. So we know they can't be negative, so you can't pick a negative 1. And you can't choose a negative 2 because those are negative numbers. But a 0 would be a good number to pick, probably a 1. Remember, you're taking the square root, so 2 wouldn't be a good number because then we'd get a decimal. And at all costs, we're going to avoid using the calculator. So you would pick a 4, you could pick a 9, but our graph is only so big. Your graphs I gave you for homework are definitely bigger, so you have more space to graph. So again, I cannot choose 0. I cannot choose 1, negative 1, which is why I started here at 0. And then I just have 1 and 4. Because the square root of 0 is 0, the square root of 1 is 1, the square root of 4 is 2. And then just plot those points. So I call this the hook graph. It kind of like hooks or curves to the right side. And it's going to the right because that's where all the positive numbers are. It is not linear because you're taking the square root of a number, so it doesn't have that same slope for each value. The difference between them will get larger as you take the square root of larger numbers. So this is what the graph of a radical function, a square root function, will look like. So every graph that you have that has a square root should have this shape. It should hook. So depending on what's going on, it might hook underneath, but it should still have like a nice curved hook. So the second graph we're going to look at, the other function, would be the cube root. So we're only going to look at two. We could do a whole bunch, but we'll look at the cube root and the square root. For these, when you have a cube roots are odd. So can you plug in a negative number for a cube root? Can you take the cube root of -1? Could you take the cube root of -8? Gavin? Yeah. So the domain can be any number because you can take cube roots of negative numbers. So the domain and the range for both of them is -infinity to +infinity. Because if you have the cube root of -1, your answer is -1. If you have the cube root of -8, your answer is -2. Because -2 times -2 times -2 makes -8. So when it's odd, you can take the cube root of negative numbers or the fifth root of negative numbers. When it's even, you cannot. And that's that even and odd property that we talked about at the beginning of the chapter. So we're also going to graph this. So generally, you want to pick numbers that you can take the cube root of. So again, you want to try and not pick values that you have to plug in your calculator. We want to choose numbers we can take the cube root of. That power sheet that we used at the beginning of the chapter, that might be helpful for you to see what the perfect cubes are. But generally, they're going to have to be small because the graph is only so big. So I would say if we could use a -8, I'd like to use a -8 so that we can kind of see the stretch of the graph. But unfortunately, the graph only goes to 5. So if you have extra room on your paper, you can feel free to put in a -8 here. Why would -8 be a good number to choose? What's the cube root of -8? Julia?
2.
Yeah, -2. What would be another good number to choose for your T-chart? What other number can we take a cube root of? Connor? -1, because the cube root of -1 is? -1. So whatever number you pick in here, we need to be able to take the cube root of it. And -8 and -1 are two perfect cubes. An easy number always to choose would be 0 because the cube root of 0 is 0. And then if we might as well choose a +1 and maybe a +8. We'll see if we can force those to work for us just so that we have a couple extra points on that graph. So cube root, you'll have negative and positive x values. Square roots, you'll have positive values. So I'm going to force this graph to work for me on the left side here. 6, 7, 8. I'll just add a couple extra boxes. So at 8, we're down at -2. At -1, we're at -1. At 0, we have 0. At 1, we're up at 1. And then if I had space, I would have another point somewhere on my side. I think you have more space on the side of yours that you can draw all that other value. So if you play connect the dots, starting on the left side, it still is a curve, and then it goes the other way, so it kind of looks like an S that you could like pull and elongate. So this top part looks like the square root graph, but since it's a cube root, we have the bottom part as well because negative numbers exist. So that's why the domain and range go from -infinity to +infinity, because it can stretch forever left and right, and it's also going to continue to creep up forever and go down forever. Questions? So the first graph that we're going to look at, we're going to throw 1/2 in front of it, and then it says compare the graph with the graph of y equals the square root of x. So we have some points here. I'm going to actually cross off the 2 and the 3 so that we can try and not use the calculator. That's my goal, to not use the calculator. Just I know it's so sad for you. See if you can plug those numbers into the equation. So take the square root of 0, multiply it by 1/2. Take the square root of 1, multiply it by 1/2. So you're taking 1/2 times the square root of 0, 1/2 times the square root of 1. I skip those two because they give us horrible decimals. So Matt, half times the square root of what is? And half times the square root of 4 is? What's the square root of 4? And half of, yeah, sorry. 2 is 1. Okay, so we're going to plot 3 points again. So we have 0. 1 is up at a half, and then over at 4, you're only going up to 1. So it says state the domain and range, and then compare the graph with the first graph that we looked at, with just the square root of x. So first state the domain and range in interval notation. Emma, what's the domain?
0, bracket 0, 2,
And the range?
0, 2.
Yeah, also 0 to infinity. That part's not changing. So still starting at 0, because I can't take the square root of a negative number, and it goes to infinity. The second part says compare the graph with the graph of the square root of x. So if you look above, here's the graph of the square root of x. Here's the graph with the 1/2 in front of it. What could you say the difference was? What's the difference between the two? I mean, the shape's pretty much the same, but what would be the difference? Connor? Yeah, the steepness. So the other one is steeper than this one. So you could say that this shrunk. That would be a good word to say, that it was a vertical shrink. You could say it's not as steep. But the other one goes up higher. So that 1/2 is squishing it down because you're taking half of the y value. You're cutting the graph in half. So if you flip the page, we're going to do one with the cube root as well. And I'm going to change this because I'm going to make these 8s again. We'll force our graph to work for us. But that avoids then getting decimals. So we're going to just force the graph. Maybe we'll even count by 2s. That might help us a little bit here. All right, so we have -3 times the cube root of 8. And then we're taking -3 times the cube root of -1. -3 times the cube root of 0. So Melanie, if you have -3 times the cube root of -8, what's that going to be? The cube, or -3 times the cube root of -1 is? What's the cube root of -1? Times -3. Yeah. And did you say 6 here? So then we have -3 times the cube root of 0. Well, that's just 0. The next one is -3 times the cube root of 1. So the cube root of 1 is 1 times -3 makes -3. And then the last one, -3 times the cube root of 8. The cube root of 8 is 2 times -3 makes -6. So if you want, when you graph it, you can either make yourself a couple extra tick marks to go out to 8, or if you wanted to, you could count by 2s. Totally up to you. So the last graph, we just added some extra tick marks, which Totally fine with. Add a couple extra tick marks. Make the graph work. So -8 up to 6, -1 up to 3. We have 1 at 0, 0, and then 1 goes down to 3, and then -8 goes down to -6. So play connect the dots. Try and make it curved. So all your graphs should be curves now. They shouldn't be lines. We're done graphing the lines. So Connor said the last one shrunk. Said it kind of just got like squished down. The steepness changed. This one is now stretching. So we call this a vertical stretch. And I'm going to flip back to that picture for the cube root graph. Right here's the cube root graph. So it's definitely a longer or a taller graph. That would be a good word to use. We'd say that taller. Here's the old graph. So this is the parent function. What else changed with our new graph? Julian? Excellent. So he said it flipped over the y-axis. You could just say it flipped or it reflected. Any of those words would work, as long as you know that it's going the opposite direction. So it's flipping the other way. It's reflecting the other way. And again, you could say it stretched. You could say it got steeper. It got taller. Any of those words work. The last thing over here to list would be the domain and the range. Rebecca, what do you think the domain is? Every single one of these graphs have that domain, no matter what. And Rebecca, the range is same. So every time you see a cube root graph, it'll always have the same domain and range. Questions? All right, so now we're going to see how these graphs can move. So we've seen how they stretch. That number in front kind of multiplies it. That gives us a stretch. We want to see how they can shift and move. We're going to skip the word problem. We'll do the word problem tomorrow, I promise, because I know yesterday I skipped the word problem too. So we'll do the word problem tomorrow, or Tuesday, not tomorrow. 3 days, 4 days from now. So it says to graph y equals a, and then the square root of x minus h plus k, or y equals a times the cube root of x minus h plus k. Follow these steps. So if you go back into your mind, we graphed parabolas in this same format. That was called the vertex form of a parabola. It had the same exact letters. It has an A, it has an H, it has a K, and it has an X and a Y. Every single graph that we do, and that you'll do next year, will have those same letters, A, H, and K. And those same letters mean the same thing for every graph that we look at. So it says, first, sketch the graph of y equals a square root of x, y equals a cube root of x. We won't necessarily do that. We're going to kind of think about what the graph will have, what it'll change, but we won't necessarily sketch that graph. But the second part says, translate the graph horizontally h units. That means h moves the graph left or right. So this moves the graph left to right. That's the number that's in the parentheses when we had x squared, or underneath the square root or underneath the cube root. So h moves the graph either to the left or to the right. And then it says vertically by k units. Well, k moves the graph up or down. And then it has the word critical point. The critical point is the starting point of the graph, the middle of the graph, but it's the important point of the graph. And that critical point would be the h and the k value. That was the vertex of a parabola. These don't have vertex values, but it's still an important point. So a critical point is h comma k. You might want to remind yourself that you need to use the opposite of h. And that was the same thing for the parabolas. Whenever it's in parentheses, whenever it's attached to x, it's underneath the square root. The h is always the opposite of what you see. So we're going to see if we can try and look at a graph that has a little bit of movement. So it's going to shift left or right. It's going to shift up or down. So looks like there are 3 graphs on this page. I think the first, yeah. So the first 2, 4 graphs actually, but the first 2 we have got one of each graph to kind of look at. So it says graph a translated root function, and then again state the domain and the range. So we have 3 and then the square root of x minus 1 plus 2. So the first thing that we are going to start with is trying to figure out what that critical point is. Because the critical point is a starting point for us to use to then try and make a graph. So if you look at the equation, I'm going to make myself a little t-chart. Does anybody know what the h and the k are in the equation? Bridget?
The h is 1 and the k is 2.
Yeah, so here is h and there is k. Remember, you're taking the opposite of h. So the h is 1 and the k is 2. That is your starting point for a square root graph, because a square root graph is the one that hooks to the right. So it's just half of the graph because it's just the positive values. So this is where our graph starts. That h and k would always be where the graph is going to start. Now we need to get a couple other points, and this is where it's a little tricky. So the points have to be bigger than 1 because this is the starting point. Because if I plug a 1 in here, 1 minus 1 is 0, and we can take the square root of 0. But we need to pick another x value that when you subtract 1 from it, we can still take the square root of it without using a calculator. So what would another good x value be, Odette?
5.
So she said 5. Okay, so let me move this up a little bit. All right, so now you're either going to have to write some stuff down because you're not using a calculator, so do a little scratch work on the side, or do some mental math. So I'm going to put my scratch work on the side. So we have 3 and then the square root of 5 minus 1 plus 2. So Odette, you chose 5 because 5 minus 1 is?
4.
And the square root of 4 becomes 2. So this is taking 3 times 2 plus 2. And Odette, 3 times 2 plus 2 is? 8. So there's my little bit of side scratch work. If you don't need to do the scratch work on the side, fine. 5 was a good number because 5 minus 1 is 4. We can take the square root of 4. I left space in between 1 and 5. What would be another good number, Gavin, that we could choose between 1 and 5? 2. So if we pick a 2, doing a little scratch work on the side here, the square root of 2 minus 1 plus 2. So the square root of 1 is really 1. And Gavin, 3 times 1 plus 2 gives us 5. You only need 3 points for a square root graph. You get any more and then it's not going to fit on the graph. So 3 points are fine. So we didn't use a calculator. We picked 3 good values, actually 2, because the 1 was from the equation. So you're picking 2 more x values. And now we're going to graph this. So starting at 1, 2, so over 1, up 2. That's our first point. This graph moved right 1 and up 2. So the movement was right and up. The inside went right, the outside moves it up or down. The second point is at 2, 5. And then the third point is at 5, 8. This is a pretty steep graph, so just do the best you can to try and connect those and make it a curved arching line. And it's just going to continue to curve upward. So now you have the graph. Looking at the graph, what's the domain? So think of the x values. Where does it start on the x-axis? Where does it go? Same thing with the range. So the range will be your y. Where is it starting for the y value? Where does it go? So Will, what do you think for the domain?
X and then to infinity.
And what is the x value? 1, yeah. So it starts at the x value of 1 to infinity. Will, what's the y value that it starts at? 2. What do you notice about that x value from the domain and the y value from the range? What do they represent in the equation? Good job.
The x value is h and the y value is
Yeah, so you're using h to infinity, and we're using k to infinity. So the x value is the h, the y value is the k. All right, I think I have time to give like one more graph in here. So if you look at the next one, we're going to try and do the same exact thing. So we're going to get a point, that critical point. So we have negative 2, and then the cube root of x minus 3 minus 2. So Maggie, what would the critical point be? 3 and negative 2. This is a cube root. So that 3 and negative 2 is the middle point. So this is the point that meets the middle of the graph. So for the square root, it's the starting point. For the cube root, it's the middle. This one's a little trickier. So now if you look underneath the cube root, we need to find a number for x that makes the cube root negative 1. We need to find a number for x that makes the cube root positive 1. So let's start with that. So what number could I plug in here to make it a negative 1? Kushal? 2. So he said we could pick a 2, which if you notice, it's 1 less than 3. So do a little bit of scratch work. So we have negative 2, cube root of 2 minus 3, and then minus 2. So the goal is to take the cube root of negative 1 because that's a number we can take the cube root of. So Kushal, negative 2 times the cube root of negative 1 minus 2. So minus 2 is 0. So negative 2 times negative 1 is positive 1. Minus 2 gives us a 0. All right, so let's pick another number. What number can we plug in for x that makes it a positive 1 on the inside? Well, Gavin, that could be a 4. So again, if you need to do a little scratch work, we now have negative 2 cube root of 4 minus 3 minus 2. And Gavin, that number would become, so negative 2 times the cube root of 1 is negative 2. Negative 2 minus 2 is negative 4. So we have a point at 2, 0. 3, negative 2. And 4, negative 4. I wanted to find 2 more points there so that we had 2 more to stretch, but it kind of connect those values. Homework, please make sure you're paying attention to the directions on the assignment sheet. Make some beautiful graphs. Have a great day. Enjoy your 3-day weekend.